That would be hard. All right, so here we go on this one, okay? So our rate laws is what we get into, right? So that we're not confused, I kind of summarize what we've done so far, okay? And so we've talked about average rate. Now, with average rate, we said, hey, we need change of a concentration over change in time. That involves two concentrations in two times. What a rate law does is it says, okay, we want to know at this specific time or this specific type of concentration, what is it right now, okay? And so we review what's happening here in a chemical equation. As we go through a chemical equation, or reaction is a better word, we have the particles colliding, they have enough activation energy to form those particular products, okay? As the reaction progresses though, you're gonna slow down because you have less stuff to hit each other, all right? And so this is kind of what our rate laws take care of. Any questions on this? All right, so here we go with rate laws, and this is what we're specifically looking at today. So rate laws are, or is an equation, mathematical equation that is going to represent the rate and the concentration of reactants. So we can't do this for products, but we can find the rate and we can also vary our concentration. So maybe we have the same chemical but a little bit different concentration. And we have a couple of new things. Number one, the rate law. When I say, hey, write the rate law, it has to follow this specific formula where we say rate equals K for constant times that concentration of one substance times the concentration of another substance. Now, this page, this slide right here, I'll have you reference back when we do some example problems. But this page right here represents the unit for K. So if I say, hey, look back at this chart for K, that's what I'm referring to here. Now, with K, your rate constant is going to be unique to what we call the reactant orders, which we'll talk about here in a second. Any questions on this? Anybody need it? Okay. All right, so now we get to this, reaction orders, okay? So number one, chemical reaction typically are gonna involve 2, 3, maybe even more reactants. And so what we're going to do is this. We are going to, from actual mathematical data, find the reactant order. Now, what that does is it tells us, okay, if we do something to the concentration, what's going to happen to our rate? So we have 3 scenarios. We can have more, and we can also have something called a 0th order, which we don't talk a whole lot about in this class, but we have reactants orders 1, 2, and 3 in our examples. So if we have a first order reactant, if we double the concentration, we double the rate. We move down here to something that has a second reactant order. And notice this is a squared value. So if we double the concentration, 2 squared is 4 times, or we're quadrupling the rate. Now down here, if we have a third order reactant, which is represented by that 3, we are going to do this. We are going to double the concentration, and we'll have an increase of 8 times. All right, so what happens? 2 root 3 is 2 times 2 times 2. That's why our rate increases by 8 times, okay? So it's all based on 2 things. What's your concentration? And also, what is your reactant order? Now this will start to make more sense as we do some examples, but any questions? Okay, now we get to this. Again, right here, the overall reactant order. Number one, this is just a generic example, but we follow the same format. Rate equals K times, in this case, our reactant A times our reactant B. And notice M and N. They're just variables. I'm just saying, hey, we can plug some value into that to find out our overall or each of our reactant order. Now, to find our overall reactant order, it becomes very simple. All we have to do is add these things together. Okay, so I'm actually going to start out with question C down here, and we'll go through this. Okay, in question C, it says, what is the overall reaction order? And so all we need to do is this. All we need to do is look back at those exponents. And so we have a 2 for NO, and it's not written, but again, in chemistry, if it's not written, generally we're going to assume that there's a 1. And so to find that overall reactant order, we just add those powers together. So in this one, the overall reactant order is 2 plus 1. And so our, again, overall reaction order, we call this a third reaction order. Okay, so this would be 2 plus 1, which is a third reaction or overall order. Now let's think about this. We're just going to break it down one substance at a time, and we'll keep going backwards here. Question B says, what happens if H2 doubles? Well, let's say we went from 1 to 2. I'm going to blank out everything else behind or to the left of H2. And so if we went from 1 to 2, 2 to the power of 1 gets us an increase of how much? 2. So if we double H2, because it's to the first power, our rate will double. Okay, so I'll put this down here for B. This is our rate doubles. Or sometimes we like to quantify this by saying 2 times. Okay. Now, up top here on question A, it says, what happens if we double the concentration of nitrogen monoxide, or NO? Okay. Again, let's say we went from 1 to 2. So now 2 squared from that 2 power, 2 squared is what? It is 4. So our rate increases by a power of 4. Or we can just say increases by 4 times. Or if you want to say quadrupled, that means the same thing. Okay? So does anybody not understand the power of those exponents? Okay. Does anybody still need this? All right. So moving on here, what we have is this. Now, this example I put on the next page. It's actually copy and paste, but I show you an example that we're going to do here in a second. How we figure out our rate law. The whole goal is going to be find the rate law, and then extended is going to be find the K. Is we have to have experimental data. Notice a couple of things. One, for each of these substances, it has the actual concentration. And then 2, it has your initial rate. Okay? Questions before we go and do a couple examples? So on our example here, okay, we're going to use the same example, and we want to do this. We want to figure out the rate law, and we want to figure out the specific rate constant for the reaction. Okay. Now, I want to start this thing out by saying, okay, we want to figure out the rate law. And so what that means is that we want to figure out this equation here. okay? And so I'm going to say this. Our goal up top here is to figure out, we want to know rate equals K times, that's times, the concentration of our first reactant, which this is a generic example. We have reactant A, and so we're going to say times the concentration of reactant A. And overall, what we're really trying to do is figure out that power that's attached with A. So I'm going to put this, we could call it X, Y, because the notes use M and N. What I'm going to do is this. I'm going to call this, I want to know what the power of M is, and then we're going to multiply it by the other reactant. So our other reactant in this example is B. We're going to say times the concentration of B, and we're going to identify, or we want to find out what that value is, or the exponent is, which again, I'm just going to follow the example and notes. We call that N. So our first priority to find the rate law is to figure out what numerical value is this M and what is N. Okay, so let's start with M first. Okay, so I'll say finding that power M. Okay, what we want to do is this, because M is attached with our substance A, we want to take a look at the chart, and we want to ask ourselves two things. One, we want to change or vary the concentration of A, and at the same time, we want to hold the concentration of B constant. So we're going to have to look at two experiments. So I ask you this, we'll start backwards. In what two experiments is B the same exact concentration? 1 and 2. Okay, 1 and 2. Everyone see how the concentration of B in experiments 1 and 2 remains exactly at 0.1. Now we're interested in what happens to the concentration of A. So I'm going to draw a line between experiments 1 and 2, and I'm going to ask you this, okay? From experiments 1 to 2, the concentration started at 0.1 and it ended at 0.2. So we asked ourselves, okay, from experiment 1 to 2, did a double, triple, quadruple, what happened in this scenario? It doubled, right? 0.1 to 0.2. If you're unsure, take the bigger number, divide it by the smaller number. So you could take 0.2 divided by 0.1, and you'd get that value of 2. Okay? So we would go through this process here. We would say, all right, in this scenario, the concentration of A doubled. What we're going to use is this. We're going to use that 2 times value, and we're going to say this. We're going to say 2 to some power M equals our change of rate. So we get 2 to some power equals our changes of rate. Okay? So because we went from experiment 1 to 2, on top here, we're going to start out with the rate, the initial rate in experiment 2, because it got bigger. So we're going to start out here on top. We're going to say, hey, this is 4.00 times 10 to the negative third M/S, and then we're going to divide that by that initial rate in experiment 1. So in experiment 1, we had 2 times 10 to the negative third M/S. Okay, so let's consolidate this. We're still going to have 2 to some power M. And if we consolidate this, 4 times 10 to the negative third divided by 2 times 10 to the negative third, or we could just view this as 4 divided by 2 is what number? 2. Okay? So now I ask you this. Now we get down to basic math. 2 to what power equals 2? 1. So what this means, this is really important. M equals 1. And so what we can call that, or what we can call substance A, is that it is a first order reactor. So substance A, I'm going to say A, is a first order reactant. Now, to help us out here, I'm going to cross out M, and now I'm going to call it 1. Now, we won't put that, but that helps us kind of remind us, hey, we're done with A. Now we got to find that power in, okay? So we ask ourselves again, for the power in, it's tagged along with the concentration of B. So we ask ourselves, B has to change. Now A has to stay the same. So what two experiments would A stay the same, but now B changes? 2 and 3, okay? So again, I'm going to look at this. I'm going to draw my arrow from 2 to 3, and I'm going to say this. Number 1, just to double check, A stays at 0.2. Okay, so it does not change. B goes from 0.1 to 0.2, and we ask ourselves, okay, going from 0.1 to 0.2, is that doubling, tripling, quadrupling? Doubling, all right? And again, if you did not know how to find that, you could take the big number, 0.2, divided by 0.1. Okay, so now we're going to end up in a very similar scenario. We are going to have our 2 for our doubling power right there to some power in equals our change of rate. So in this time, again, because that experiment 3 was our bigger number, our bigger concentration, we are going to have this. We are going to have 16 times 10 to the negative third m/s all over 4, experiment 2, times 10 to the negative third m/s. Okay, so again, we consolidate this down. We say 2 to some power n equals what happens when we take 16 divided by 4. We get 4, okay? So now we're in the driver's seat once more. And so we want to find out what that power in is. So we ask ourselves, 2 to what power equals 4? The second, okay? And so this is really important. Our n would equal 2. Remember, n's tagged along with that substance B. So that means we can say this. We can say that substance B is a second order reactant. And once more, what I like to do is I like to say, okay, I know N, it's a 2, and now I can write my rate law. So my rate law, I'm going to write just above this box, and I'm going to say this. I'm going to say, all right, my rate law that I found using experiments is this. We have to write rate equals lowercase k times the concentration of A, and then I'll ask you this, A was what reactant order? First. Now, over here I put a 1 just to remind us, but when we write the actual rate law, we leave it just as A with no power because we assume that it's a 1 up top there. Then we multiply that by the concentration of B raised to what power? Second, because it is a second reactant order. Okay, so right there, what I have in purple above the box, this is the rate law. Okay, now we just got one more part, and it's not overly difficult. We want to find that specific rate constant. Okay, specific rate constant, that is a K. Okay, so here is what we want to do. We want to do this. We want to pick one experiment, and we're going to plug those numbers in. So we can have experiment or trial 1, 2, or 3. What experiment do you guys want to do? 1, all right, too easy. So I do this. I always circle everything in experiment 1 so I don't confuse myself. Now all I'm going to do to find that value of K for constant is plug these values in. So I'm going to look at my rate, and I'm going to say, hey, in experiment 1, it was 2 times 10 to the negative third m over s, molarity per second. And so for my rate, I'm going to start down here, and I'm going to say, okay, 2 times 10 to the negative third m slash s is equal to, we don't know K, so I'm going to leave K just as that, K for constant, times our concentration of A, which is 0.100 raised to that first power, which we don't need to put, times the concentration of B, which is also 0.100. However, we need to raise that to the second power. Now I'll ask you this. How do I get rid of the stuff attached to K? Divide, okay? Now, I will tell you, be really, really careful when you divide, and it's because of that exponent, okay? So I'm going to write that down. If you want to start solving it in your calculator, that's fine. But we would take 0.1, and I'm putting these in brackets. Obviously, you can't put brackets in your calculator, but make sure that when you put this in your calculator, that squaring is just attached to that 0.1 of substance B. Okay, so we have that divided. Now we can find K. And does anybody have this calculation ready? What is it? It's exactly 2, okay? So I'm going to put 2.0, just have that extra 0 there. And then I'm going to ask you to turn back to that chart that I said, hey, remember K, I'll tell you to reference that chart. And I'll ask you this. Overall, what is our total reaction order from this rate law? So look back at the exponents. We have a 1 plus a 2. So 1 plus 2 is 3. So we're looking for the third overall reaction order. And what's the unit associated with that K? There it is. M to the negative 2, S to the negative 1. And again, you're going to get that chart. I'm going to provide that to you. So that way you don't have to worry about knowing what the units of K are. Questions? All right, does anybody still need this? All right, let's go a little bit faster on the second example. I give it to you in a pretty similar format. There's some differences here. The one difference is now we have real substances, not just substance A and B. And the other thing is I give you 6 trials or 6 different experiments, okay? So we'll start out with this. Again, the first thing that we want to do is we want to establish that generic rate law and then actually find our particular rate law. So up top, right here, I'm going to put down this. We want to find out our rate law, which remember, rate equals K times the concentration of our reactant, NH4 plus ammonium, okay? NH4 plus, and we want to know, hey, what is that power M? Times our other reactant in this particular reaction. And so we're going to say times NO2 minus our nitrite ion. And we want to know, hey, what is that power, which we're going to just give it as the variable N. Okay? And so we start out with this again. Right, we want to establish or find out our M value, okay? So we ask this, for M, to find M, we want to look at experiments where we change around NH4, but we hold NO2 minus constant. Right? So somebody give me an experiment where we change the value of M, or we change the value of NH4 plus, but hold NO2 minus constant. 1 and 2, okay? So for this, between experiments 1 and 2, again, I always like to verify, hey, NO2 minus is 0.2 for both of these. So we ask ourselves, from experiment 1 to 2, the NH4 plus concentration went from 0.01 to 0.02. So we ask ourselves, relatively, did it double, triple, quadruple? Double, right? So we say, hey, this is 2 times. And so what we're going to do is this. We are going to say, all right, 2 times, or 2 some power M equals our change of rate. Again, because our concentration got bigger in experiment 2, on top we're going to start with this 10.8 times 10 to the negative 7 M over S. All divided by the initial rate in experiment 1, which is 5.4 times 10 to the negative 7th. And I'll ask you this, all right? We have 2 to our power M. What happens when we take 10.8 divided by 5.4? We get 2. So 2 to what power equals 2? 1. So M equals 1. That's fine and dandy. But what does that mean about NH4 plus? What can we say about that?
The first order reactant.
Very good. First order reactant. Now, again, just for my reference, I like to say, hey, I know M, it's a 1. Okay? We do the same thing for finding N. So we say, all right, we need to find N. So we ask ourselves, where does NO2 minus change, but NH4 plus stays constant? 4 and 5, all right? So in 4 and 5, I like to do this. Again, I like to verify, okay, NH4 plus stays at 0.2 and 0.2 in experiments 4 and 5. And then I look at NO2 minus. We went from 0.0202 to 0.0404. So did it double, triple, quadruple? It doubled in terms of concentration 2 times. And so we say this, all right? We say that we have 2, because it doubled, to some power n equals our change of rate. Now, because experiment 5 was the bigger concentration of NO2 minus, we're going to start with that rate on top. So we're going to say, all right, 21.6 times 10 to the negative 7th m over s, all divided by that rate in experiment 4, which is 10.8 times 10 to the negative 7th m over s. Our 2 to the n power equals, what's that number become? 2. 21.6 divided by 10.8 becomes 2. So again, 2 to what power equals 2? 1. So n equals 1. But what does that mean about our nitrite ion? Very good. Okay. So now we get to our rate law. Rate, again, we always have to write it like this. I'm going to write it in purple again above. Rate equals K times the concentration of NH4 plus. Do we need to put anything above that? No exponent, because it's first order reactant. And then we multiply that by the concentration of NO2 minus. Do we need to put anything above that? Okay, this right here, once more, that is our rate law. Okay, so to find K, what do we need to do? Plug in a trial, plug in an experiment. What trial do we want? 1. All right, too easy. So again, I'm going to circle experiment 1. And I'm going to start out with our initial rate, which is 5.4 times 10 to the negative 7th m over s equals K. We don't know K. Times the concentration of NH4 plus, which is 0.01. We raise it to the first power, and then we say times the concentration of NO2 minus, which is 0.2. We raise that to the first power there. And so now how do we get K by itself? Divide it by what it is attached. Now, this is nice because we don't have to worry about exponents here because they're both first order reactants. All right, so can somebody help me out? If we take 5.4 times 10 to the negative 7th divided by 0.01 times 0.2, what do we get? Yeah, can you put that in scientific notation? One more time, 2.7
times 10 to the negative.
2.7 times 10 to the negative 4th. And then we look back at our chart. First off, overall, this reaction is overall what order? 2, because 1, x1 of 1 plus 1. So overall, it's a second order reaction. And so what is our K unit for something that is second overall order? Perfect. M to the minus 1, S to the minus 1. Okay? Any questions here? All right.